Um, Again, thank you. I'm Dr. Dr. Muhammad Salah, and I will be co-chairing with Dr. Muhammad for this session. I'm assistant professor at Sultan Qaboos University. In this session, we have 3 presentations. So we are going to start with the first one, energy retrofitting of the public transport bus station in UAE by Abdussalam Al-Dawood, Fatima Muhammad, Tabarak Khalid. I don't know who will present. I think Fatima, you are there.
Hello.
Hello.
Yes, hello everyone. Thank you so much for having us today. Actually, my friend Fatma will host the meeting. The presentation is going to be from her laptop, and I'll start the meeting immediately if everything's ready. Okay. Shall I go ahead?
Yeah, please.
Everyone.
Yeah.
Shall we start?
Yes, please.
Okay. You can see my screen, right?
Yes.
Yes, for sure. I see.
Okay.
Yes, please go ahead.
Okay. Shall we go?
Yes, please, Fatima. Please start.
So hello everyone, and welcome to our presentation today, which is about energy retrofitting of the public transport bus stations in the UAE. This is Tabarak Khalid talking, and my colleague Fatma Muhammad will be sharing the presentation with me today. So in today's presentation, we will give a short review about the study, and then we will be moving on to the construction and the energy analysis of the building. And then we will talk about the methodology that we have followed during our study. And finally, we will demonstrate the results and discuss the final solutions that we applied on this project. So the opportunities for energy saving and reducing emissions by retrofitting existing bus stations in the United Arab Emirates is very significant, especially for the energy demand and space cooling, which are growing faster than any other building sectors. So in general, we have the HVAC system and the artificial lighting system requirements are considered a major portion of the total energy consumption in the transportation buildings. Thus, from that perspective, we took the Abu Dhabi bus station as a case study, and the design builder software was utilized in order to investigate the impacts of various retrofitting measures for air conditioning system and, of course, for the building envelope in order to achieve the main objectives and select the best courses of action in order to reduce the energy consumption and CO2 emissions for the public bus stations in the UAE. So our building is actually located in the United Arab Emirates, Abu Dhabi, the capital of the UAE, and it was opened in 1989 by the Bulgarian architect George Klarouf with a total area of 50,000 square meters. Of course, the building, as it's very old, it has lots of problems in terms of envelope, in terms of the energy consumption, and also in terms of the functions and circulation inside the building. So why did we choose specifically the bus station? Because it's an important landmark in Abu Dhabi, and there are a huge number of users that are using it daily, which is about 10,000 passengers per day. And as I said before, it lacks from a lot of important functions inside the building. So our records was actually based on studies and statistics from the Department of Transport. For example, in figure 3, as you can see here, there is a forecast for the upcoming 25 years old for the number of users in the building. So actually the building is a bit crowded, and we need to enhance the overall, let's say, environment of the building, especially inside and outside the building. And also, according to the Tourism and Cultural Authority of Abu Dhabi, the bus station considered as a heritage building. And here are some figures which shows the overall envelope and the shape of the building itself. So for the existing condition of the building itself, as you can see in figure 5, there is a lack in the ceiling and insulation of the building, and the external walls was constructed only from reinforced concrete, cement, and paint with no insulation. Moreover, the external windows were generally a single glazing system, and the HVAC system that has been used is a package system, as you can see in figure 5 down, that we're putting it outside the building, so the air supply and return ducts come from indoors through the building exterior walls. Moreover, the daily consumption of the building is very high, and the mainly consumers is the HVAC system of the building. Again, the building itself lacks of so many facilities which are required for a bus station in order to enhance the overall performance of the building. As you can see here in figure 6 to 8, for example, people are waiting outside the building, so immediately we can notice that there are not enough places for people to wait inside, and they are actually maybe having their luggages with them, so there are no luggage places and lots more another important functions for a bus station to have. So that's what we tried to solve in our proposal. So in the proposal that we had, we tried to solve the interior functions of the bus terminals in order to ensure a high building performance. Also, the existing package system will be replaced in a variable air volume system in order to ensure that we are improving the energy performance of the building, and we can see this later on in the later stages of this presentation. We have some statistics that really prove that there is an enhancement in the overall energy consumption. Also, there will be improvements and repairs done to the air distribution system, and also in order to ensure keeping the ductwork in a good condition and to prevent the air leaks and air energy loss. And again, the most important thing for the architectural characteristics and the overall envelope shape, including the roofs, walls, windows, they should be developed in order to ensure we have a higher insulation materials and install a high performance windows. And figure 9 and 10 shows actually the proposed overall shape from the exterior and the interior.
Moving on to the methodology that we followed for this research, Design Builder software was used to create a base model for the case and multiple alternatives, as you can see in figure 11. The aim is to define and employ the performance of several retrofit scenarios and their impact on reducing the energy consumption of the case, and reach the optimum retrofitting scheme. Several retrofitting techniques are investigated, including improving the thermal properties of the building envelope by adding EIFS insulation system, which is exterior insulation finishing system, and reducing the building cooling load by enhancing the efficiency of air conditioning and distribution system in the building. As you can see in figure 12, simulated model on Design Builder shows a deviation of 2.3% from the actual consumption of the existing building. Here we have 6 different scenarios, which compares between each 2 alternatives that we talked about earlier. In first scenario, we applied the EIFS insulation system to the existing walls, and we changed the single glazing system, which used in the existing building, to the double glazing argon-filled glass, which resulted in a reduction of 53.1 megawatt hour per month. And in scenario 2, the second scenario is to replace the existing HVAC system, which is used in the building, which is package system, to the central system, which is more efficient for the public areas in terms of the energy consumption, and with adding the EIFS insulation to the building envelope, which gives a reduction of 68 megawatt hour per month. In the third scenario is to change the existing lighting system, which is used in the existing building, to the LED lights, which is more efficient, and to improve the building envelope by adding the EIFS system. This scenario gives a reduction of 39.3 megawatt hour per month. The fourth scenario shows a reduction of 58.9 megawatt hour per month, which is a result of improving the HVAC system and changing the glazing type to the double glazing. Next scenario is to add double glazing system for the existing building and changing the existing lighting system to the LED light. This scenario gives a reduction of 38.8 megawatt hour per month, which is not really good compared to the other scenarios. And finally, the last scenario is to change both HVAC and illumination system of the existing case, which reduces the energy consumption up to 52.8 megawatt hour per month. Moving on, figure 19 shows a chart which shows the energy consumption before and after each alternative is applied. And based on this chart, changing the HVAC system reduces the energy consumption with the higher percentage, which is about 33%. And the second most efficient alternative is to improve the building envelope by adding EIFS insulation system, which reduces up to 29% of the total energy consumption. Thus, after analyzing the 6 scenarios, the second scenario was selected as the best case scenario in which it had the highest amount of reduction among the others, so that scenario is selected to follow in order to enhance the overall energy consumption of the existing building. And here are the references that we use for this research paper. And thank you all for listening, and I hope you enjoyed this presentation.
Thank you very much for this nice presentation. Let me be clear of that we are going to continue the whole presentation. We have 3 presenters today, and at the end we will have a 15 minutes for question and answer. I remind all attendees that you can post your questions in the chat, and then it will be forwarded to the presenters at the end. Thank you very much.
Thank you so much for having us.
Thank you.
Thank you so much.
Thank you very
for
much
listening.
Now let's move to the second presentation. Numerical simulation of the hot and cold flows produced by a room heat pump for personal comfort and energy savings, by Hatan Wu, Ahmed Al-Badi, and Yang Zhang.
Yes, but it says I can't share my screen with others sharing it right now.
So you will be so please wait.
Sorry, can you stop sharing the screen?
Yeah, fine. So please, where is Fatima? So please, could you please stop sharing?
Yeah, of course. Sorry for the
Thank you very much. Yeah.
Welcome.
So, Houghton, could you please start?
So, can you see my screen right now?
Yes, it's clear now.
Yeah.
Please start.
Let's go ahead. Hello, everybody. Before we begin, let me introduce myself briefly. I'm Hao Tian, and I'm a postgraduate student who currently studying PhD about combustion in University of Sheffield. I'd like to talk to you about the numerical simulation performance of an in-room air source heat pump, which deliver both hot and cold flow into the room. First of all, I will introduce the background and literatures about the heat pump topic. Then I will talk about the turbulence mode and the geometry of the integrated air source heat pump and the surrounding environment. I will continue by comparing the plotted results of the air source heat pump and electric fan heater with the same power output. To finish, I will make some conclusions according to the simulation results. So let's get started. In regions having cold climates, a heater is one of the essential amenities in your home in winter. As an inexpensive, simple, and straightforward way of generating heat, electric heaters are commonly used in student accommodation in the UK. However, the thermal efficiency of heat pumps is better than the purely electrical heaters. A conventional heat pump collects energy outdoors and uses refrigerant to transfer the energy into the room. But both heating methods always have a problem that heat heated air gathering from the roof to the bottom. Thermal comfort is hard to reach without big power consumption. Furthermore, the three traditional types of heat pumps, namely air source, water source, and ground source heat pumps, all require the installation of an outdoor unit and often have frost problem. Next, let me introduce some previous studies. Researchers on air source heat pump heating methods have been focused on optimizing the performance of air source heat pumps in terms of frost resistance, heat gain, and energy savings. Some of them use low carbon energy sources to promote less carbon dioxide emitting. Some have compared the temperature and velocity distributions between the traditional heating methods. Some studies have found that the heat pumps are 22% and 33% cheaper than air and floor heating. This project therefore attempts a numerical simulation of an integrated air source heat pump in a room in combination with a ground-mounted air conditioner. This heat pump operates in a similar model to a reverse circle refrigerator, blowing heat from the heat pump directly to the body while simultaneously exhausting cold air to the other side. A preliminary CFD mode was developed and attempts are made to analyze the heat distribution. Again, this project aims to numerically simulate the flow pattern of an integrated air source heat pump, which delivers both cold and warm air to the room, in order to find an integrated air source heat pump design which can reduce electricity consumption on the one hand and gives the occupants a satisfactory level of thermal comfort on the other. After the background, let's talk about the turbulence mode I had used in my project. The main differences between the standard capsule mode and the realizable capsule mode are the new formulation for the turbulence viscosity and a new transport equation for the dissipation rate, epsilon, has been derived from an exact equation for the transport of the mean square vorticity fluctuation. The advantage of the realizable capsule mode is the precision of predicting the spreading rate of both planar and round jets. For the cases involving rotation, boundary layers under strong adverse pressure gradients, separation, and recirculation, the realizable model normally gets more accurate results. The research simulation focused on a simplified room model with a size of 3.2 times 3.5 times 2.5 meters squared. In order to simplify, some assumptions were made. First, the heat pump has heat transfer on the exchanger. However, it was ignored and modified to be two constant outlets and one pressure inlet. The rotation of the fan blade was also not being considered. The airspeed was constant in the modeling. The pressure drop between outlets and inlets is not considered in the simulation. The flow was assumed to be compressible to analyze the buoyancy effect of hot and cold flow in the room. The human body in this case was considered to be adiabatically thermostatic with no humidity conditions. The heat pump and human body was modeled as shown and placed 0.6 meter away from the wall. Comparison group of same-powered electric fan heaters were built. Only boundary conditions were modified. So let's move on and discuss the results. First, let's have a look at the streamlines. The presence of the heat flow was felt in the lower body when a person sits in this position, while the heat flow was also perceptible in the upper body due to buoyancy effect. After passing the target, the heat flow diverges to the sides of the target and gathers on the roof. Then the airflow on roof was pushed towards the other side of the room by accumulating heat flow and met the cold air flow which is moving upwards and was eventually drawn into the inlet of the heat pump. This figure clearly explains the difference of two types heaters models. The color of the streamline is depending on the temperature as well as the surface contour. It is obvious that heat pump can produce higher temperature than the electric fan heater with the same power. However, this is the same outlet velocity. The buoyancy effect of the heat pump case is larger due to larger temperature difference. This has been overcome by adjusting the hot flow direction. The nozzle structure helps the heat exchange between cold flow and the environment. To clarify the flow field, velocity vector on plan was presented. The color for figure 5 represents the air velocity. The length of the vector represents the magnitude of the vertical component. The vector both pass over the sides of the body and rise to the ceiling, propelled back behind the heater by the later airflow, and will finally drawn into the heater. As both heaters have a large outlet area and a small inlet area, the velocity reaches a relative high value at the inlet, but as this does not have a particular large effect on the room heating results, so not much more was discussed. By increasing the downward velocity of hot flow, the buoyancy effect was overcome, enhancing the heating effect on the body at 1.5 meter at lower air velocities. Without the direction adjusting, the hot flow will bend and cause no heating effect on the feet of the body. The wind speed close to the body is around 0.7 meter per second, which is acceptable. Next, looking at the temperature control on the same plan, the heating effect on the longitudinal direction can be observed. The nozzle structure helps the dispersing cold air currents and reduces the cold air area. Large hot outlet area helps distribute the heat evenly to the body. The temperature difference on the body was about 3 degrees of Celsius. The electric fan heater was 5 degrees of Celsius less warm than the heat pump, while distribute temperature field evenly. The hot flow can bypass the body, creating a surrounding comfortable field in both cases. Now we shall take a look at the surface on the body which doesn't face the heater. The heat pump has more temperature difference on this side of the body. From the plan control vertical to the heating direction, it can be found that most heat was concentrated on the target. This results in a more efficient energy usage compared to radiator and floor heating. Last, let's look at the horizontal control of temperature. Large temperature difference can be observed in the heat pump results. Comparison of the floor plan temperature plots reveals that only electric model raises the temperature of the floor air. Heat pump model has lower floor temperatures than the original room temperature in the space beyond the heating target, but the heating effect was concentrated on the target, thus forming a uniform temperature distribution on the body 1.5 meters away. In terms of the thermal comfort, all the models showed an evenly distributed temperature control on body surface. At this point, I'd like to turn to the conclusions made from this project. First, the comparison reveals that for such an integrated heat pump, the heating effect is generally better than that of an electric heater of the same power over a certain distance. There were two contradictions in its setting of temperature and flow rate. The first is the pursuit of high COP to save energy, leading to greater temperature gradients affecting thermal comfort. And the second one is as buoyancy plays a significant role. If outlet airspeed is increased to reach further targets, it will lead to high airspeed affecting thermal comfort. And then such an heat pump can satisfy thermal comfort for the side of targeted body facing the heat source, while the other side's thermal condition will change with physical environment. The integrated air source heat pump should be easier to install than a normal heat pump. The heating is instant and does not face frost problem. The heating capacity for a certain range of frontal areas was more effective than electric heaters of the same power, saving on electricity consumptions. And here is the reference of this project. And that's all for today's presentation. Thanks for listening.
Thank you very much, Hatan, for this interesting presentation. Again, I just remind you that we are going to ask the questions by the end of the session. And thank you for Dr. Saleh. You have a lot of questions for us. Now, could you please unshare your screen so you can start the next one? The next one is evaluating the effect of ceiling diffusers on airflow patterns in an office space to achieve effective air distribution. I think, Sijal, you are here.
Hello. Yeah.
Hello, you're welcome, Sijal. So could you please
Thank you. Yes.
Sharing your screen? Yeah, now we can see your screen. Yeah, please go on. Thank you.
Okay. So the year was 2020, and for the first time, I realized how critical was indoor air quality and its effects on human health. I am Sejal Shanbhag, a recent graduate in Building Energy Performance from CEPT University in India. I currently work as a building services consultant and come from a background in architecture. I carried out this study during my master's under Professor Rsm Algorithm, an assistant professor at CEPT University and program chair of the Master of Technology in Building Energy Performance. The people spend 90% of their daily life indoors, and now even more so due to the widespread influence of the pandemic. The contaminants generated by these people disseminate through aerosol dispersion, and the transmission of these contaminants occur through air distribution. Many researchers describe controlling exposures as a fundamental method to protect people indoors. Center for Disease Control and Prevention gives a hierarchy of controls, with elimination of the source being most effective. At the same time, it's not always practical. Engineering controls include ventilation, filtration, disinfection, temperature and humidity controls. The focus of this study is on ventilation, which has 4 major components: indoor air quality, quantity of fresh air, air distribution, and pressurization. ASHRAE, further, the air distribution is divided into various techniques or categories, which is displacement, underfloor ventilation, you have personalized and overhead mixing. Now in India, the most used ceiling diffusers are square, round, and the vortex diffuser. Now ASHRAE 62.1 suggests an air change rate of 6 to 10 for office spaces. For this, the air is distributed with various techniques as mentioned earlier. Now most of these offices are designed with overhead mixing ventilation due to diluting the air, and as per ASHRAE handbook, we have there are these 3 that are most used. Now, similar studies have been carried out for hospitals, labs, clean rooms, which have fixed occupant generated contaminants and function at a much higher air change rate. In this study, I have considered a small office space used in the ASHRAE project 949 of dimension 5.16 meter into 3.65 meter and of height 2.43 meter. Now the furniture layout includes 2 cabinets, 2 tables, and supply and return ceiling diffusers. The space is occupied by 2 people as heat sources and 2 computers and 4 lamps. It also includes an east-facing window, and the boundary conditions are considered as follows. It is all the temperature and velocity profiles are measured at 5 poles at 4 different heights along the center line of the room as shown here. For the office space, the airflow patterns are mainly affected due to the room geometry, which includes the dimension, furniture layout, and the orientation. The supply diffuser, its location and the types. The supply flow rate, the inlet velocity and the diffuser dimension. The return diffuser, its location and its type. The heat sources within the space, their location, the lighting equipment and the occupants. And the contaminant sources, their location, the rate of generation of the contaminant, and the number of pollutants within the space. In this study, the variable parameters are the diffuser types and their locations. Further, computational fluid dynamics is carried out using ANSYS Fluent in a workbench environment, and it mainly comprises of these 5 steps: development of the geometry, meshing, setting up the boundary conditions, and CFD solving, and then analyzing the results. The supply and return diffuser in this study are ceiling mounted with area factors as per the manufacturer's data. A contaminant source is modeled at the person 1. Now, based on the throw characteristics of the 3 diffusers that we considered, a range of the supply and return diffuser location is considered with a minimum distance constraint of 1.3 meter between the supply and return diffuser. For the meshing, tetrahedral structure is used, and a mesh sensitivity analysis to demonstrate the grid independence is carried out for 4 mesh resolutions. The result of the resolution 5 and 6 showed only a variation of 0.15%. However, resolution 6 required an additional 1.5 hours of computational time on an 8-core processor. Resolution 5 with a 1.5 lakh elements is taken forward. Now, the 3 diffusers are set up with fixed parameters considered as follows, and one source of occupant, person 1, was set up as a contaminant inlet of carbon monoxide. The transport equations are solved using RNG K epsilon model set up to achieve a residual value of 10⁻⁻⁶. This model was considered after validating or different types of models and then selecting the RNG K epsilon model for this particular geometry. Now, to evaluate the air distribution, 3 metrics are calculated. They were air diffusion performance index, or ADPI, to satisfy the effective draft temperature as per ASHRAE 55. An ADPI of 80% is recommended for office spaces. And this was measured at 216 points along the grid shown here at 4 different heights in the occupied space of this office space. Now, air change effectiveness, or ACE, is calculated to study the effectiveness of the diffuser in supplying air to the room, and age of air is added as a user-defined scalar in ANSYS, and the average is measured in the breathing zone. Now, for the ventilation effectiveness, it is calculated to study the effectiveness of the diffuser in removing the occupant-generated contaminant. The average concentration was measured in the breathing zone, and an exhaust concentration with a probe at the return diffuser was measured. Now, the objective here is to find a design maximizing ADPI, ACE, and the VE. For this, virtual optimization is carried out with response surface model using the Mode Frontier platform. Optimization parameters earlier discussed are considered as inputs, and a Mode Frontier workflow was set up to integrate ANSYS Fluent using the API. The workflow is divided into process flow and data flow. The application nodes couple the components to compute the outputs based on the inputs. Design of experiments. The DOEs are considered using 2 sampling methods. Urban Latin hypercube covers the entire design space, and the incremental space filler added new points to fill spaces uniformly with a maximum criterion. A total of 38 DOEs were selected based on the input parameters. Each DOE is simulated and required over 114 hours for simulation. The sensitivity analysis detects which independent variables contribute most to the variability of the dependent variable, and the least contributing variable can be set as constant. The algorithm SS ANOVA ranks the input parameters by giving relative importance for the given data set. Now, since the supply diffuser position and the diffuser type had maximum effect on ADPI and ACE as seen here, and the return diffuser position had maximum effect on ventilation effectiveness, all the parameters are accounted for. The virtual optimization based on RSM is performed. It approximates the relationship between the input and output variables. This saves on the computational power and time. An approximation algorithm was used in RSM training, where all the DOE results are used in the training. Now, sensitivity of the RSM algorithm were compared to select the best fitting algorithm. Data points are added to the added if the performance indices do not achieve the acceptable accuracy. Two algorithms were found to be best fitting, ACE and ADPI. Results were predicted by the radical basis function, RBF, with an R-square value of 1. The Gaussian processes, GP, predicted the VE result with an R-square value of 1. To run the virtual optimization, PILOPT, an Esteco proprietary multi-strategy optimization algorithm, was used, and following this workflow, the optimization design is validated by solving using ANSYS Fluent. Now, an average error of 0.8% was achieved. The aim is to achieve error percentages close to 0, and if not satisfied, the process is repeated with increased number of iterations. The global optimum result is considered after verification. The output variables are evaluated with trade-off between air diffusion performance index, the air change effectiveness, and ventilation effectiveness to obtain the optimum designs for each diffuser type. The plan represents the location of the supply and the return diffuser for the local optimum designs in the office space. Now, the local optimum design for the round diffuser failed to achieve the 80% minimum criteria for air diffusion performance index, and also indicates the mean concentration in the breathing zone to be higher than that at the exhaust. The square and the vortex diffuser achieved similar values for ADPI and VE, but the ACE value was 33% higher for the square diffuser. Square diffuser achieved a global optimum value for the supply and return diffusers, which is placed in these locations at a distance of 1.8 meter from each other. Looking at the conclusion of this study, for this particular geometry, the square diffuser achieved good results in effective air distribution in the room to remove the for the removal of the contaminant, achieving a ACE of 0.51, ADPI of 81%, and VE of 1.1. The supply diffuser position impacts the airflow patterns in the room based on the heat sources and their locations. The return diffuser placed close to the occupant is effective in removing the occupant-generated contaminant. The methodology used in CFD and virtual optimization can be further used to optimize supplies and return diffuser locations in different office spaces. Further, the study can be looked into achieving experimental validation of the optimum result, increasing the number of input parameters, and the study of office spaces of different sizes. Thank you. I would like to express my sincere gratitude to Mr. Sandeep and application engineer at Esteco Software India for virtual optimization through machine learning algorithms using the Mode Frontier platform. And I would also like to thank Professor Rajan Raval, Professor Yash Shukla, and Professor Meenu Agarwal, and also Mr. Nikhil Singh, who have sincerely contributed time, support, and valuable suggestions for this study. Thank you.
Thank you very much. Now, Dr. Muhammad will handle the Q&A. The floor is yours.
Thank you. Thank you. Thank you very, very much. Thanks to the presenters and our audience. Please, if you have any questions, use the chat box to post your questions, and then I will read them for the presenters. So maybe I will start with the questions that we already have. And the first question to Fatima. Please, Fatima, if you could unmute yourself. And I wanted to ask, what was the result of combining the best alternatives in one solution? For example, you considered building envelope, you considered HVAC, the type of illumination system. Did you come up with a one final scenario for your design renovation?
Yes, actually, as we said in the conclusion, the best scenario was the scenario 2, which was the HVAC system, changing the HVAC system from the package to the central, and with changing or adding the EIFS insulation system to the building envelope. And this results in a reduction of 27% of the total consumption of the existing building.
Great, great. And can I ask what type of materials you used for the building envelope? I mean, what did you change in the envelope? Was it only the insulation or the other materials that you used?
Actually, the existing wall is only cement and plaster. So that's why we use this EIFS insulation system, that we applied the insulation from the exterior walls on the existing building, because we cannot touch the walls. So we added this insulation from the exterior walls in order to reduce the energy consumption.
Great, great. And in the final design that you were showing, I saw a very new design, a very pointy corner with lots of glass. How do you see using so much glass when you want to reduce the energy consumption? Did you use a very specific type of glazing in your final design?
Actually, we use double glazing for the part, because the existing part was the classic part that you can see from the 3D, and that was in the architecture point of view, the other concept. So we tried to combine these both, like the architecture and consider both retrofitting and the architecture point of view. And that much of glass, it's like we use the different techniques to avoid using
overheating. It's fine. It's fine.
I guess she meant using a tinted glass. Yeah. I don't know. I guess the voice has been over from there.
Okay, good. Good. Do you have anything to add, Tabarak?
Well, we would love to share our full proposal so you could see and compare the architectural part and the construction part, let's say, and you could see the enhancement of the overall shape of the building in terms of function, architecturally more than, let's say, from the sustainable. So you could see how we did change the whole shape of the building and how we made a huge contrast from an old heritage building and contrasted with the very, let's say, new, unique building to make it more as an iconic thingy in the capital of Abu Dhabi. Great. We would love to share it really, and we want to know your feedback about it.
Of course, your paper is on the website, so that's very great, and we hope this could initiate new changes in our traditional.
Can you hear me? Sorry.
Thank you very much, Fatima, and
Tabarak. Thank you. Thank you so much. Thank you so much
for your responses. So I go to the next presentation. Thank you very much, Hushan. Your presentation was very interesting. I had 2 questions, if you could unmute yourself, and it was mostly about your simulations, how you performed, how you run the simulations. How was the CFD model validated? Have you considered any any types of validation for this interesting safety simulation?
Yes, for the first question, it's a proof of concept study and there's no experimental data for validation. So it just proves the concept.
Mm-hmm. And are the grids different for the ASHB and the electric fan heater models, or they are the same?
No, the only difference for the ASHB and electric fan heater models are the boundary conditions. For the electric fan heaters, I just cancel the cold outlet and change the boundaries in Fluent.
Good, good.
So
And it was,
the grids are the same, yeah.
Great. It was an office building that you modeled, I guess.
Yeah.
Right. Great. And when you were comparing different these two heating systems, you were referring to air velocity, the temperatures in 3 layers, and if we want to come up with one suggestion, which one would you recommend for using the office? If we want to recommend one of these heat systems, which one at the end you recommend?
Yeah, for energy saving, of course, the heat pump can produce more heat and using less energy. Well, while the effect is very evenly distributed, so I would recommend the air source heat pump in this project.
Great, great. And we received another question. What was the supply air temperature did you consider for heat pumps for comfort evaluation?
Sorry, what was the supply air temperature? Can you rephrase that or clarify?
Maybe I guess maybe this question is more related to the next presentation, but I see that your presentation is very aligned with the next one, which we are considering pollutant removals in office buildings. And if we have contaminants in office buildings, how air circulation could spread or avoid contaminants in office buildings. Thanks, Haoshan. If as the last question, if we want to perform this research for residential buildings or other types of activities in a room, will you change your heating systems? Will you recommend further research with different types of heating systems?
Yeah, I would surely recommend further research because the geometry of the room would affect the cold flow very large. The cold flow was very dependent on the geometry of the activity of the room and the activity of the target.
Absolutely, absolutely. Thank you very much, Haoshan. So the last question will be to Sejal Sanjay. Please, if you could, yeah, thank you for unmuting yourself. Maybe this last question is more related to your study. What was the supply air temperature you consider for heat pumps for comfort evaluation?
Yeah, so the supply temperatures I have considered are for ceiling diffusers, and I have 3 different ceiling diffusers. So for each of them, based on the office geometry, the supply velocity was considered based on the CFM required. And for the square diffuser, it was 5.2 meter per second. For the round, it was 3.58 meter per second. And the vortex was 7.5 meter per second. So it was considered based on each of the diffuser type.
And the contaminants that you used were coming from the main source of air, I guess. If our
So the whole concept was that the people in the room are the contaminants, and so my contaminant source is at a human breathing level, at the mouth and the mouth opening, and the velocity of the contaminant, which was considered, was based on a particular study where they have found out what is the opening of the mouth and the velocity of a single cough. So based on that, I have considered the velocity and the opening aperture area for the human being, which is my contaminant in the space. So in this study, the contaminant not from the supply diffuser, but as a contaminant source separately within the room.
Great, thank you very much. And as you know probably better than me, we have other sources of contamination. For example, the carpets, sprays, could
VOCs and different microbes. Within this thing. So this study was looking into only the human contaminant. So I have in the CFD model, the contaminant is the human. So we are trying to find out how long does it take for that contaminant to exit the return diffuser, and try to optimize the position of the supply and the return diffuser in such a way that we can utilize the same system that we have for better removal of the contaminants, instead of going for a different system altogether, where we would require higher capacities so that they supply more outdoor air percentages. So this study was mainly to identify not completely replacing a system, but for an existing office space, trying to identify what would be the best supply and return diffuser locations.
Great, yeah, thank you. I'm sure your topic would be very interesting for everyone in these times of COVID pandemic. So thank you very much. And could you, as my last question to you, could you also model opening windows to see how opening the windows and having fresh air could reduce the amount of contamination? Is it possible to model it in your simulation tool?
Yes, that would be a further study where we also consider right now what in this study I've just considered a supply and a return diffuser. And you can also include, whereas my window was closed, the east facing window in the office space is considered closed. So, and only heat gain, it's only considered as a heat gain as it's an external wall. But we can also consider it as an inlet of fresh air where the occupants would be able to open the windows such that some cross ventilation or natural ventilation could help further reduce the contaminants in the space.
Thank you very much, Sejal. That was very great. I really enjoyed all these 3 presentations. Please, if you have any question, everyone, please use the chat box. Otherwise, I just wanted to thank you, thank the presenters and the panelists, and please, Dr. Mohammed Salah, please, if you have any.
Thank you, Dr. Mohammed. I think we got some questions. They covered all the presentations. And thank you all for these interesting topics that you presented today. And wish you to see you in the next keynote session, inshallah. Okay. Thank you very much.
Thank you.
Yeah. Thank you.
Thank you.